Hi, Algebra 2 honor students. Today is Unit 12, Day 4. Today we are looking at solving exponential equations. So the only way we really know how to do this up until this point is maybe graphically by doing y1, y2, calculating some intersections. But now that we know a little bit more about logs, we can use logs to very easily solve for x in these equations that you're seeing right at the start of the notes. So if you are getting yourself set up here, we are going to be solving for x, and we're going to round our answers to the nearest hundredth. So the very first example here says 3 to the x equals 4. So in order to solve, if we take the log of both sides, I think the best case scenario for us is to take the log base 3 of both sides. And this is something that we did kind of briefly in the notes yesterday. And the reason why taking log base 3 makes the most sense, of course, is because the base of the log or the exponential term is 3. So if I asked you, hey, what's log base 3 of 3 to the x? The answer is x. And wow, that was one quick step to get x alone. X is now equal to log base 3 of 4. Now, what is that rounded to the nearest hundredth, though? Remember that when you go to see where the button is for log on your calculator, this is log base 10. It's not log base 3. So from yesterday's notes, we have that new change of base rule. So you could actually write this as x equals log 4 divided by log of 3. So if you want to use just log base 10 on the calculator, log 4 over log 3 is equivalent to log base 3 of 4. And that winds up being 1.26 to the hundredths place. So 1.26 is the answer here. Now, I should let you in on a little secret, though. And this is a function that when I started my teaching career, I know I'm old now, but this was not available on TI calculators. But since it's now available, I might as well show it to you. Ready? If you hit the math button right here, hit math, you're going to then scroll up. Remember we used to do like summation in Unit 10? That was kind of a new big deal for us. Look at what option A says. It says log base. If you hit enter for log base, you can now enter whatever base you want. We want log base 3 of 4, and that's 1.26. So you don't have to use change of base. I will tell you change of base has its uses. So later on, especially when you get to calculus, you'll need to know the change of base rule. Your teachers, if it's me, will expect you to know that, all right? Because there's other things that you do in calculus that involve this rule. However, for now, if you like that log base function, I'll probably use that to round to the nearest hundredth. All right, let's go on to 4 to the 2x equals 17. So for this one, same idea that if I want to isolate and get rid of that 4 to the power, you're going to take the log base 4 of both sides. So over here, log base 4 of 17. When I do that, log base 4 of 4 to the 2x is just 2x. That equals the log base 4 of 17. And finally, in that last step, we just have one quick additional step to get x alone, which is dividing by 2. So log base 4 of 17 over 2. By the way, this is called an exact answer. Sometimes I might ask for the exact answer, so you would leave it just like that. But to the nearest hundredth, let's get fancy with log base. Here we go. So it's going to be math and then scroll up to option A, log base 4 of 17. And then if I take that and divide it by 2, we get the final answer of 1.02 to the hundredths place. Okay. So last but not least, in number 3 there, if you have a base 6 for your exponential, let's go ahead and take log base 6 of both sides. Okay, so if you take log base 6 of both sides, log base 6 of 6 to the power is the power, 3x plus 1. On this side, you get log base 6 of 243. So this one just has 2 additional steps to get x alone. First one, of course, is subtracting 1 to the other side. 3x equals log base 6 of. I'm going to throw that 243 in parentheses now, because when I subtract the 1 over, this does not become 242. Okay, you have to take log base 6 of this number, then you can subtract 1 from it. And finally, last step is to divide by 3. So x would equal, in an exact form, log base 6 of 243 minus 1 divided by 3. It's a lot to say. I'm going to do a fancy fraction for this one. So let's on the top put log base 6 of 243. Get out of there. Subtract 1. Divide by 3. And the final answer to the hundredths place is 0.69. Okay. So hopefully after going through these three examples, you should become very comfortable solving exponential equations. It really does not matter what the base is. Just choose a log of the same base on both sides. And then in some cases, like in numbers 2 and 3, you might have one or two quick additional steps to get x alone. Well, in each of those cases, I'll tell you at the top, the base of that exponential was alone. There are times where maybe you need to isolate the base first. Okay, so that base 3, that base 4, that base 6, they were already kind of alone. I mean, there was different things up at the exponent, but that was fine. Let me give you an example of what I'm talking about here. If I gave you 2 times 3 to the 4x minus 1 plus 5 equals 13. Okay, this looks a lot more complicated than what we have up above, but I'll tell you, it's really not that different. But you do have to take some steps to isolate the base of this exponential first. First step is, let's subtract the 5 to the other side. So 2 times 3 to the 4x minus 1 now equals 8. Okay, next, do not multiply those to get 6. That's really bad because then you're breaking PEMDAS. Got to do exponents before you would multiply those. So since I don't want to multiply the 2 in there, let's divide it to the other side to get 3 to the 4x minus 1 now equals 4. All right, and once you get down to the step where you've now isolated the base, now you can introduce a log. So let's take, if it's base 3, log base 3 of both sides. So here we get log base 3 of 4. Log base 3 of 3 to a power is the power 4x minus 1. Okay. And then 2 more steps to get x alone. We're going to add the 1 to the other side. Log base 3 of 4 plus 1. And then finally divide both sides by 4. Okay. So you guys can get practice typing this into the calculator. If you're curious, this answer is 0.57. Okay, but otherwise, if I said leave your answer as an exact answer, I would have stopped here anyway. Okay. So hopefully you can appreciate that this really isn't that many more steps. You just have a couple quick steps to isolate that base 3. All right, let's try another one like that. You're going to like this one. Ready? 2e to the x plus 1 equals 10. Ooh, base e. I like that one. Okay. There's actually just one quick step to isolate the base of this exponential, isolate the base e, and that would be dividing both sides by 2 to get started in this one. So we very quickly get e to the x plus 1 equals 5. All right, so what am I going to introduce on both sides in order to get rid of this base e? Well, instead of writing log base e on both sides, we know that log base e is very special. Log base e is ln. Okay, the natural log. So I'm going to take the natural log of both sides. And the ln of e, which again, this is log base e, of e to this power is the power, x plus 1. That equals the natural log of 5. And then it's really quick to get x alone, just subtract the 1 over. Again, don't subtract the 1 from that 5. It's not ln 4. It is just ln of 5 minus 1. To type this in, we do have that special ln button right here, right next to the 4. So ln of 5, and then subtract 1 from it. The rounded answer would be about 0.61 for this one. All right. So solving exponentials can be as easy as these examples as far as just isolating the base and then introducing a log on both sides. Well, I said it can be as easy as that, but certainly we can amp up the level of difficulty. Here we go. Let's solve this one. 2 to the 3x plus 1 equals 3 to the 4 minus x. Okay. Now, there are a few different approaches you could take for something like this. The approach that I'm going to take is I'm not going to play favorites. And what I mean by that is that both sides are exponential right now. Right? This isn't some constant on the other side, which it has been for each of the other examples. So I'm not going to take log base 2 of both sides, and I'm not going to take log base 3 of both sides. Okay, you actually could do that and still get a correct answer. But because I can't make a common base, and I don't want to choose one of the bases to match these exactly, I'm just going to take good old log of both sides. And remember, when I write log of both sides in this example, we're talking about log base 10 here. And how is this going to help me solve for x? Well, if you take the log of both sides, what that will do is it's going to take this exponent, don't forget about angry birds, and bring it to the front. So we're going to bring those down kind of to like level playing fields here. The 3x plus 1 is going to get brought in front of the log of 2. And then the 4 minus x is going to get brought in front of log 3. All right, so once you're at that stage where you've brought those exponents to the front, now you can distribute log 2 and you can distribute log 3. So I'm going to distribute log 2 through here. I'm going to distribute log through 3 there, because remember, log of 2 and log of 3, those are numbers. Log base 10 of 2, log base 10 of 3, those are actually values. All right, so we get 3x times log 2 plus log 2. On this side, you get 4 log 3 minus x log 3. Okay. So now that we've distributed the log 2 and the log 3, we're kind of at a key stage with, if you want to solve for x, we have x's on both sides. So the key stage here that we want to do is group the x's together. So anything with an x, you're going to put on one side of the equation. Anything without x, you want on the other side. So essentially, I'm going to switch the order of these two terms right here. I'm going to add x log 3 over here. I'm going to subtract log 2 to that side. And I am going to do it in one step because I know you guys can handle that. But it's going to be 3x log 2 and then plus x log 3 here. And then on this side, 4 log 3, subtract the log 2 over there. So I've accomplished my goal of getting the x's together on one side and then anything that doesn't have an x on the other. And why do I want to do this? I want to do that important step because if you have all the x's together on one side, you can now take out x as a GCF. Okay, our whole goal is to solve for x. So let's go ahead and factor out x as a GCF. That leaves me with, from the first quantity, 3 log 2 plus log 3. And on the other side, 4 log 3 minus log 2. Okay, we're one quick step away from getting our answer. If you divide both sides by this quantity, 3 log 2 plus log 3, your final answer is 4 log 3 minus log 2 all over 3 log 2 plus log 3. And that looks like a pretty intimidating answer, right? At this point, it might be a question where we wind up rounding to the hundredths place like we have in the others. Let me just see what this is to the hundredths. So if I do, oops, not that. Let's do a fancy fraction here. We've got 4 log 3, and this is just log base 10, right? So minus log 2. The denominator, 3 log 2 plus log 3. To the hundredths place, that winds up being 1.16 approximately. Now, I'll tell you, I kind of get fancy with these. And I'll tell you the reason I'm going to get fancy is that my answer on my key probably doesn't look like this. Because if you have multiple logs being subtracted on the bottom and then maybe added on top, you can condense each of those to single logs. Remember, this would be 3 to the 4th if I angry birds that exponent up. 3 to the 4th is 81. And then subtraction would condense to division. So that's 81 halves up in the top. Down here, it would be 2 cubed, which is 8 times 3, and 8 times 3 is 24. This answer just looks a little bit cleaner to me. Is it a necessary step? Not really, but I can justify it to you real quick that that is the same answer. If you do log of 81 halves divided by log of 24, that should be, fingers crossed, there it is, 1.16. So if you are checking answers with me, typically I will condense the logs in the end. Okay, maybe not always. I might even break the rule in the next one, but I do think this happens to look a little bit cleaner. Okay. All right, let's do one more. And I understand that's definitely more challenging than the ones we did on the front, but the last solve that we'll do is solving something of the form 3 to the x times 5 to the 2x equals 271 to the x plus 1. Okay. So this This one also will present its challenges to us. We have 3 different types of exponential bases. We have 3 to a power, 5 to a power, 271 to a power. Holy cow. 271 really escalated things, didn't it? All right, let's go ahead and use the same strategy that we did in the last one. Let's start by taking the log of both sides. So when I take the log of this side, it's log of this whole thing, 3 to the x times 5 to the 2x. Same thing, log of this whole side, log of 271 to the x plus 1. Okay. So we know the properties of logs that we're going to wind up using here. Similar to what we saw in the last one, we know that those exponents can come to the front, but we have one additional thing to consider here. On this side, not only do the exponents come to the front, but we have multiplication happening. And when I expand multiplication, we know it expands to addition. So just to kind of remind you of that step, this is the same thing as log of 3 to the x plus log of 5 to the 2x. Okay, and this is what we have on this side. Okay, now in that same step, could you have also brought the exponents down? Sure, I'm just doing it in 2 steps here, just to really kind of make sure that we're okay with that step. But it's now x log 3 plus 2x log 5 equals, bring that binomial x plus 1 out front, and that's in front of log 271. Okay, a couple additional steps here to make sure that we can get all the x's on one side. It's the same strategy from up here, group the x's, and then get a GCF. All right, so let's see, x log 3 plus 2x log 5. On this side, if I distribute log 271, it's x log 271 plus log 271. Okay. So, couple steps away, I'm going to subtract this to the side. I already have 2 terms with x over here. Group all those x's together. X log 3 plus 2x log 5. Now it's minus x log of 271. That equals log 271 on this side. Okay. And then last but not least, now you can take out an x as a GCF from all 3 of these. So that's log 3 plus 2 log 5 minus log of 271. Okay. And the last step, again, to get x alone would be divide both sides by this whole quantity. So we have a lonely log 271 up top. The bottom is log 3 plus 2 log 5 minus log 271. Okay, and I am going to break my own rules and kind of leave this as is. The rule that I'm breaking is I just condensed it earlier to single logs. I could do that on the bottom, right? It'd be 3 times 5 squared divided by 271. It's just not a nice number. So I'm going to leave it as is, okay? And this is an exact answer. Pretty easy to type into the calculator if needed for rounding purposes, okay? So that's some good exponential solving. I mean, this is as hard as it gets in this exponential part. So you'll see a lot of stuff that's very similar to the start of the notes, but will we see some questions like these two sneak their way in? I would say so. All right, so you'll be ready for it though when it comes up. If you have any questions about the solving techniques you've seen today, please let me know, and then have a great rest